So when we do calculus, the first concept we have to understand is the concept of a limit. What limits do is that they allow us to ask about what happens at a certain point without reaching that point. So an example of that would be, what happens to the value of the function when we get closer and closer to a certain x value? Because there's going to be some functions that we deal with that aren't defined at a certain point, but we can confidently say, what is the limit as it approaches x is equal to whatever we're looking for? So the limit allows us to do that in a mathematically sound way, even though we don't know what happens at the specific value. Okay, to see how limits work, let's go ahead and consider the function f of x is equal to x squared. So here I've drawn out the function and I've chosen a table of values. So 0, 0 is our first point, and then 1, 1. So then from 1, 1, we go from 1 to 2, but I've chosen some values in between 1 and 2 to show the progression. So as we go from 1 to 2, the function converges to the value of 4. So 1 to 4. It takes a while, but these values eventually get to 4. And then going the other way, from the right, from 3 to 2, we see that it goes from 9 and goes down until it also converges to the value of 4. So this is what I mean when I say what happens as we approach the value x is equal to 2. What happens to the function? Well, the function converges to 4. Now, that shouldn't surprise anyone because that is the value evaluated at 2. That's just 2 squared. But let me go ahead and define another function. We're going to call this f2 of x. And we're going to define this slightly differently. It's going to be pretty much the same function with one variation. So we're going to split this up. And I'm going to define for all values x is not equal to 2. And then I'm going to define another function for when the value of x is 2. So when x is not equal to 2, I'm going to say that the function is still x squared. Now, when the value is 2, I want to define it differently. I want to say it's 7. So now this chart is no longer valid, and neither is the graph. So how do we change that? Well, we see that for every single x value that isn't 2, so that's everything on this side, and that's everything on that side except 2, we see that it's still x squared. So everything else here still holds. The only difference is when x is equal to 2 at this point, well, now I've said that it's 7. It doesn't obey x squared. So now this function sits here. That's the value of the function as I've defined it. So in order to fix this, because we can't have 2 values for every one x value, we're going to draw a little hole. This denotes what's called a jump discontinuity. So the function now is discontinuous, but it's still defined at that point. Now this is still mathematically correct because for every x value, I've given it a y value. So now, let's go and look at the chart. Well, everything up here, all of that is still valid. And everything from 2 to 3 and so on, that is still valid because it's not x is equal to 2. And so the only thing that's not correct about this chart is at the point x is equal to 2. Now, that needs to be changed to 7. So it doesn't look like what it should because I've defined this function now a little differently. But let's go ahead and ask the question anyways, what happens now to the function as we approach 2 from either side? So the way we're going to think about this when we write this as the limit as x approaches to of now new function f2x, well, what's that going to be equal to? Well, let's go and look at it numerically. So if we just worry about the values that are not 2, we see, well, numerically, it still approaches a certain value. It's going from 1 to 2 to 3 to 3.8. It's getting closer. From down here, it goes from 9 to 6.25 to 5.06 to 4. And so on. So we see that even though we don't necessarily know what that is at 2, we can say, well, it looks like it's approaching 4. That's what it's doing, not knowing what happens at 2. So this is where the limit comes in handy, because we also see graphically here that it does approach 4, right? We just are saying, well, it's not defined the way we think it is at x is equal to 2. Now we're saying it's 7. So in this case, the limit is still equal to 4. So this is the reason why limits are so useful, because there's going to be times where we don't know what the value of the function is defined at 2 in this case, but there's going to be other types of continuities, and we're not going to know what happens at those points, but we can use the limit and see, well, first graphically, well, it's still approaching 4. Like, that's just what the function's going to do. Once we get to 2, it jumps up because I defined the function that way. So this, in essence, is the reason why the limit works and it's useful.